Yes. Okay, so we are recording, and I think you can simply start with the presentation. Please go ahead.
Okay. Good morning, everyone. As Eckhard introduced me, my name is Masanori Shukuya, and I used to work for Tokyo State University for more than 35 years. And my original background was architecture. And you may imagine that those who graduated from departments of architecture usually involved in architectural design, structural engineering, and so on. But I was very much interested in the environmental and energy issue in the built environment, so that my major started with architecture, was combined with thermodynamics and also human biology. And today, the next 50 minutes or so, I would like to talk about what we have found through our research over the last 30 years or something. And there are quite a lot of technological and also quite deep scientific things that you may find a little bit difficult to understand. But I would like to try to make my talk as easy as possible. And what I would like you to find today is the importance of connective thinking. I think that you are now learning quite a lot of disciplines from the social science side to natural science side. And the very, very important thing is to develop yourself the ability or capability to make connection between one discipline and the other discipline and so on. And that is what I have done over the last 30 years or so. And that is what I'm going to talk about today. And in my title, you find low-exergy, not energy, exergy. And I'll tell you why not exergy, not energy, but exergy. You know, we are now facing environmental and energy issue, and energy is to be called exergy. So I would like to explain why exergy is necessary, and also before going into the exergy theme, I'd like to share with you the image that we are now facing. Now you can see two drawings that is made by myself, and left-hand side, you can easily see that something like gear is the head. And this man or woman hold human's head. Of course, this is a cartoon, but something similar to this is going on all over the world, I think, in human society. We are very much surrounded by the technology, and that is one thing that we can do such online lecture and online meeting and so on. Very, very convenient and very, very nice. But if we rely too much on computers and other things, then something like left-hand side would happen. And now I think that we are facing such a thing. That is the cause of so-called energy and environmental issue, I guess. So we need to go to the right-hand side. Science and technology should be handled with our hands by humans people. So this is also what I like you all young people to think about, looking into the future. So today's theme, built environment. You are all living in a house, maybe condominium or a detached house or wooden house or concrete made house and so on. So built environment, this is our closest environmental space. And we spend more than 90% per one day, not only at home, but also classrooms in school buildings or cafe in the town area and so on, more than 90%. And if we assume one person lived for 100 years, this means over 90 years we spend indoors. That is why we call built environment the most immediate environment. And that immediate environment should be conditioned nicely for human being. This is, I think, universal all over the world. So let us think how light, heat, moisture, air behave indoors in relation to outdoor environment. That is the science that I have been involved. And over the last 35 years or so, I have been involved quite a lot of things in the field of building science. And this is one drawing that I drew in 2015. This is the image that resides in my head, how I look at the built environment in relation to the global environment and universe. We call it nested structure. As you can see here, there's the human body. The center of the temperature is 37 degrees C, and we are surrounded by built environment, and built environment is surrounded by urban environment, maybe fisherman's village or farmer's village and so on. But anyway, Koganei, Yokohama, and also Tokyo area, urban area. So we assume that this is urban environment. And urban environmental space is surrounded by regional environment. And the biggest regional environment is global environment. And global environment, the temperature, the average temperature is around 15 degrees C. North Pole, South Pole, much lower. The southern part, the equatorial area, maybe a little bit higher, but average 15 degrees C. And so-called global warming problem is that this temperature is seemingly increasing over the last 70 years or something. But we don't know whether it really goes up much higher or start going down. Anyway, this temperature, 15 degrees C, the average global environment temperature, is mainly determined by the solar radiation coming from the sun, and also thermal radiation going out into the universal space, whose temperature is minus 270 degrees C. Very, very cold space area. So high temperature, the sun, 5,700 degrees C, and very cold universe. The global environmental system exists between high temperature and very low temperature. And you know that there is the air circulation as you feel wind outdoors and indoors, and also water cycle as you experience rainfall or snow and so on. And rain comes from the clouds, and clouds are formed within the atmosphere, and it is very much influenced by the galactic cosmic rays and in relation to solar wind. This is just like the indoor environment. When you feel very hot, you may close the curtain. If the indoor space is rather dark during daytime, you may open the curtain. So you control the indoor environment by doing like this. The same happened in the global environmental system on the Earth. What I'm saying is cloud. Sometimes very fine day, sometimes cloudy. This is dependent. This is very much related to the increase and decrease of global environmental temperature. So it is very important for us to understand how the nature works and find the way of building built environment and the way of our life. So as I already explained to you roughly, the radiation takes place outside and inside the global environment. And left-hand side, there are three graphs, and the left-hand upper graph is the solar radiation coming from the sun. The horizontal axis shows the wavelengths. Light radiation, this is the electromagnetic wave, so that there is the wavelengths. So solar radiation has this kind of characteristics. And left bottom graph shows the thermal radiation. We are surrounded by the indoor space and also outdoor environment. The temperature is usually from -20 to 60 degrees C, usually from 10 to 30 or 35 degrees C. So the radiation we are surrounded has such characteristic. Quite similar curve, but the wavelength is quite different. The solar radiation wavelength is in the unit of micrometer from 0.3 to 1.0 or something. On the other hand, indoor space, the wavelength is around 10 micrometer, quite long. And outside the Earth, we are surrounded by the very, very cold space, and there exists background radiation, which is very, very tiny amount of radiation, and wavelength is very, very long. So that is what we are surrounded by, the very different radiation with very different wavelengths. Okay, so today I only have 15 minutes to give you the talk, so that I cannot go into the detail of a lot of things. But before going into the built environment, I'd like to briefly introduce Earth, what kind of space Earth is surrounded. Right-hand side, this is the Earth. And in the middle drawing, Earth is made smaller. And now we can see that Earth is surrounded by the magnetosphere. Earth is a kind of magnet, as you know, North Pole, South Pole. And the sun gives solar radiation in addition to solar radiation, and solar wind is a kind of particle rays made of the protons. That is the cause of the north light and southern light in the North Pole and South Pole. And the solar system is surrounded by heliosphere. So these are the very big size of the environmental space that we should know before going to discuss the environmental issue. And over the last 15 years or something, the cloud cover, the amount of cloud surrounding the atmosphere is very much influenced by cosmic ray. And that is made by, you can see the name Svensmark in the right bottom. Professor Svensmark is the professor at the Technical University of Denmark, and he is the pioneer of the cosmoclimatology. His research area is to make connection between the cosmic rays, solar wind, how the clouds within the atmosphere is made, and so on. And he found that the sunspot number, sunspot, like this. This is the picture of the sun. You can see the black spot. The number of sunspot and cosmic ray and cloud cover are very much related. So that is why I said indoors, we close curtain and so on. The same happened in global environmental system. But this is not done by human being, but the nature does. Over the last 20 years or maybe 30 years, everybody has discussed global warming and so on. And now in Scotland, COP26 is now being held. The main issue is global warming and how to reduce the CO2 emission from the human activity. Of course, it is very important for us to take a look at the CO2 emission from the human activity and reduce the overuse of natural potential given by fossil fuels. But the true nature of global environmental system is not determined, probably, not only by the human activity. The nature has its own characteristic. So if we keep increasing the emission of CO2 gas, then it may help the nature occur some catastrophic phenomena that should be reduced. This is one of the reasons that we should be very, very careful to make use of fossil fuel and so on. But I'm a little bit skeptical that some people, even scientists, and even very influential politicians who may be very much influenced by some very influential scientists, all the cause of global environmental issue, especially global warming, is caused alone by CO2 gas emitted by human activity. We don't know yet whether it is true or not, but reduction of the fossil fuel is important anyway. That is what I'd like you to share with me, I would say philosophy or thinking. So talking about the environmental technology, much can be seen in the nature. So this is the chicken baby, and you must eat almost every morning or every evening the chicken egg. So how chicken egg comes to chicken baby? This is the drawing of is under development. Starting from the embryo, the chicken baby is born in the end of 20 days with the nicely taken care environment. And as you know, the shell can transmit oxygen, transmit CO2. Otherwise, chicken baby cannot be born because it cannot breathe. So shell is not the, we human see the eggshell, there is no open window and so on, but there are a lot of tiny windows over the shell. Such is the very basic passive technology. I would explain what passive technology is later. And blood vessels, without any help by mother chicken and father chicken, independently, the fertilized egg develop itself by itself to be baby chicken. And they develop their own heart, blood vessels, vein, artery, and so on. And within 20 days, the fertilized egg becomes chicken baby. So blood vessels, together with heart as a pump, this is we call active technology. Okay? And passive and active, you may find the characteristic passive and active like this. Left-hand side, you can see yacht. On right-hand side, the boat. Boat has engine. Yacht has no engine. Why yacht can move further? Because there is a wind. So wind is caught by the sail and then move. In the case of boat, the wind may reduce its speed. So you may not like the wind when you are on the boat, but in the yacht, wind is welcome, unless it is like storm. So passive technology is to make use of the natural environmental resources in immediate environment. And active technology usually rely on fossil fuel. Fossil fuel is coming from very far remote place. So passive and active, that can be seen in the very origin, the origin of such technology, passive and active in baby chicken. So it is very important for you all to take a careful look at the nature in your very immediate environment, not only indoors, but also outdoors. And you can find quite a lot nice examples and give you some hints. And passive technology has a long history in the human being. So passive technology is very much related to the regional environmental characteristic. For example, here in Japan, especially in Kanto area, winter season, coldness is rather mild, but as you know, in summer, very hot and humid. Some other places all over the world, some desert area, dry and hot, but not humid, and so on. So building types are quite different, as you can see in the two photographs in the upper side. And active technology, which was very much developed over the last 100 years, we can have the technology that we can build such high-rise buildings. High-rise buildings, these two twin tower buildings may be seen not only in Tokyo area, but also in San Francisco, Singapore, China, almost everywhere. Very universal. Not different according to the climate. Passive technology, you can see the difference. But active technology, you can erase the difference. That is the very nature of passive technology and active technology. So good combination of passive and active technologies are very, very important, I think. So my major was, I already explained to you the building science, and it is very important for us to know how to build it again, the passive technology, and how active technology should be combined with passive technology. To do so, I saw that we need to know about the internal environment, how it is related to external environment. Internal environment, that what I mean is the environmental space inside our body. And energy issue, energy is the concept of physics, and the key feature of energy is to be conserved, not consumed. So the legitimate concept to be able to accurate what is really consumed is exergy. So two things that are I mostly focused in my education and also in my research career. So next 25 minutes or so, I'd like to introduce you why internal environment is very important for us to take a look, and what can be known from the exergy concept in relation to so-called energy issue. The last two lines here in this slide is the message for all of you looking into the future, next 10 years, 20 years, and so on. We need to advance the passive technology by renewable. Renewable, what I mean is not only renewable energy, but we need to renew the passive technology, which was inherited from the old buildings, and to advance that can fit with the contemporary architecture, contemporary buildings. And active technology should also be redesigned to be able to suit to advanced passive technology. So far, active technology was developed very much independent of passive technology. And you can see what happened by this. Extremist active system is the nuclear power plant. And we all need to avoid this kind of catastrophe, and we shouldn't rely on this type of technology. And this accident was the fact that we human beings too much relied on active technology, ignoring the merit of passive technology. So this is what we should learn from this that happened 11 years ago. So as I told you, internal environment, this graph shows the internal environmental temperature inside your body or inside my body. Blue line, this is the eardrum temperature, and gut, rectum, underarm temperature. Well, the blue line is the average of 20 students while I was working for Tokyo State University, and red marks are given by the English physiologist who made this measurement with one subject. The important point is that you can see the fluctuation. Early in the morning, the temperature becomes very low, not very low, but 35.5 or 36 degrees C or something. Late afternoon, it becomes higher. So this fluctuation is quite similar to outdoor temperature fluctuation. Why this kind of fluctuation is given inside our body? This is because evolution takes place over the last long years from the birth of the very simple organism. And in the very beginning, environmental temperature is the body temperature. But gradually, the evolution gives us homeotherms. Homeotherms is the animals whose body temperature almost constant, but never totally constant, but like this fluctuation. So this fluctuation, very small fluctuation, is the reflection of the environmental temperature fluctuation outside our body. So this shows that we humans are part of the nature. One other example that I can tell you in terms of the nature existing inside our body is biological clock. This graph is comes from Kleitman and Engelmann, very old stuff. They measured, or they recorded one baby when he or she slept and when it is not asleep. So black horizontal line shows while he or she in sleeping mode, and open area awake mode. So you can see some pattern like this. So the top line, 11 days since the birth, 90 days, 120, and the last bottom line, almost 180. So between 150 and 180, you can see that this baby sleep during nighttime and daytime awake. But in the early days, from 11 to 90 days, such a pattern cannot be seen. So what happened? And this is the major data of tidal height in the Yokohama Bay Area. And you can see the swing of the tidal height. The 0 is the average, and sometimes higher, sometimes lower. Spring tide, neap tide, spring tide, neap tide, and so on. So over the 1 year, it fluctuates always like this. This is because the gravitational force becomes different from day to day because of the position of the sun, the earth, and the moon. So this data is taken from the Japan National Weather Bureau, and I remade like this. The horizontal axis shows the 24 hours for one day, and open circle and closed circle, the low tide and high tide. Low tide and high tide means this is high tide and low tide. So dot mark gives high and low. And then I try to compare these two graphs. And you can see I drew two lines, and you can see the characteristic of the sleeping and awake mode is very similar to high and low tide in the nature, in the baby. So the baby's cycle, waking up and sleeping, are quite similar in the first 90 days or 120 days. Tidal circulation, tidal fluctuation. So this gives us the idea that the biological clock, this is the internal nature in harmony with external nature. So we humans are part of nature. That is very important for us to take a look. And when lighting is designed, such a human nature should be taken into account. But so far, lighting design is made only take a look at electric lighting, no window effect, and so on. That is very much problematic, and we need to take a look at the combination, nice combination of daylighting. Daylighting is the lighting with windows and electric lighting. Both are to be in harmony with each other. Okay. One other thing that I'd like you to know about is the exergy characteristic of the human body. Human body emits a lot of heat, as you can find yourself in the early in the morning in the bed, in your bed. When you go out for bathroom, for example, early in the morning and coming back to your bed, you must feel very warm with your blanket and your bed. This heat originally comes from your body. And this slide gives you some comparison. How much smaller or larger the heat coming out from the human body and heat coming out from the sun. Of course, the sun gives huge amount of thermal energy, so that the direct comparison is meaningless. But why don't we divide the body by body weight? Q human, our metabolic energy emission rate divided by body weight. Similarly, overall radiant energy emission rate from the sun divided by mass of the sun. And the answer is, surprisingly, 10,000 times larger in the case of human body in comparison to the sun. Of course, the total amount of heat coming out from the sun, much, much bigger than the human body, but the thermal energy emission rate per kilogram is human body much, much larger. Why I'm saying this is that because of this, it is very important for us to get rid of the heat from the human body, not only during summertime, but also during wintertime. And 4 routes can take place: convection, the movement of air, and radiation coming from the wall, radiation going out from the human body, and also conduction. If you put your hand on the computer or desk or wherever, you may feel a little bit hot or maybe a little bit cold and so on. So that is conduction. And we sometimes sweat. So that is evaporation. So these 4 paths of heat transfer always take place to control the body temperature. The body temperature has to be always, as I already show you, like this. Our body temperature has to be between 36 to 37 degrees C. Over 37, our body malfunction. Lower than 36 degrees C, again, malfunction. So we need to control our body temperature at a certain range. And this is automatically done by our brain and also our body. So my research done over the last 20 years or maybe 25 years, that is exergy. And I cannot go into the detail of exergy today, but what I found from the use of exergy concepts, which is quite interesting probably to you in relation to the human body temperature regulation, is what I'm going to talk about today within 12 minutes or something from now. So very briefly, why exergy is necessary? There are 2 tanks, one bigger one and one smaller one, 4 times larger, and 5 liter is smaller one. So suppose that we raise the temperature in the larger tank from 20 degrees C to 40 degrees C. Smaller tank, 20 to 100. Probably in the lecture given by Eckhard, you may be able to calculate thermal energy contained by these 2 tanks. Thermal energy becomes totally the same, 1,674 kilojoule. So so-called energy issue, if we discuss with these numbers, then you may find something strange. Suppose that your right hand goes into larger tank, left hand into smaller tank. Just imagine what would happen. Your left hand would be burnt very severely, but right hand, you may feel very warm and comfortable. But the energy amount, the amount of energy are exactly the same. So something is missing. That is why exergy is necessary. I cannot go into the detail of the exergy calculation today, but in these 2 small examples of the tanks, 40 degrees C larger tank had 55 kilojoule of exergy, and 100 degrees C smaller tank has 194 kilojoule, larger exergy. So I said my hand would be burnt with the 100 degrees C tank. This is consistent with the amount of exergy. So exergy, not energy. Exergy is the true nature of the resource. So that is why we need exergy to especially discuss the so-called energy conservation, energy saving, and so on. Because exergy can articulate what is really consumed. So one other example, there is a 5-liter water with the wheel and the weight. The weight goes down and then wheel can be turned around. So there is the friction, and friction gives you some heat in the tank so that the temperature, the water temperature can go up to 100 degrees C if you put the sufficient distance, the height, and also sufficient amount of weight. So exergy, 100 degrees C water or 5 liter has 194 kilojoules, but potential exergy, while the weight is high up in the top, 1,674 kilojoules. This is exactly the same as energy, but exergy is reduced. Why? Because friction is the exergy consumption. So so-called energy consumption is by exergy, the friction and also dispersion, that kind of energy is legitimately expressed by consumption like this. So turning around the wheel gives a lot of consumption. That gives you 194 kilojoules of thermal exergy, warm exergy, to warm up your or burn your hand and so on. So with this conceptualization, we can know how lighting system works, how heating, how cooling system works, how ventilation system works, and so on. And what I like to show you today in the very last moment of my lecture today is the human body exergy consumption. As I told you, human body emits some heat by radiation, convection, conduction, and evaporation. And inside our body, the temperature should be kept around 37 degrees C or something, not higher, not lower. So to keep all that things, the blood circulate, and also sometimes when you feel cold, you wear a sweater, or when you feel a little bit hot, you remove your shirt or jacket and so on. So to control the human body temperature. So how human body exergy consumption rate are related to thermal environment, especially in winter. So our thermodynamic nature of the human being are very much related to these 8 factors. First, radiant temperature. It may be the first time for you to hear the term radiant temperature. Just suppose this is the average temperature of the room, the ceiling, wall, floor, window, the average temperature of the surface. Within the room space, there is air. So of course, air temperature affect the heat transfer within the body. Air velocity, when you feel very hot, you usually do like this to feel cold, because air temperature is usually lower than body temperature. So air velocity enhancement gives you some heat emission so that you may feel a little bit cooler. As you know, humidity also affects very much. So these four things, radiant temperature, air velocity, air humidity, these four are the components of the environment, the very immediate environmental factor. And then metabolic heat rate, whether you are sitting or whether you are walking, whether you are running, the energy emission from the body is quite different. And also, as I already explained, what you wear without just the t-shirt or some sweater or that kind of things, clothing. And then outdoor temperature and outdoor humidity. All those factors influence the human body. And this figure shows the relationship mean radiant temperature and exergy consumption rate within the human body. Mean radiant temperature is just suppose that this is the temperature of the average surface temperature of the room space. And vertical axis shows exergy consumption rate. It may be a bit difficult for you to imagine what it means. Just consider this as the thermal stress of the human body, thermal stress of the human body. And there are four kinds of plots: 14 degrees C, 18 degrees C, 22 degrees C, and 24 degrees C. This is air temperature, okay? So take a look at the mean radiant temperature between 10 degrees C and 15 degrees C. This is the case in winter time, and ceiling, wall, glass window, floor, very cold from 10 to 15 degrees C. So in such a case, you must need heating. Usually you switch on your air conditioning unit or maybe stove and so on. So air temperature has to be increased from 14 to 18 to 22 and 24. So between horizontal axis 10 to 15, you can see that the raising the air temperature gives you lower exergy consumption rate. This is to reduce the thermal stress from your body. Yes, rather than 14 degrees C, 18 degrees C is better, 22 degrees C is much more better, and 24 is better. But take a look at the horizontal axis toward right-hand side. If the mean radiant temperature becomes over 20 degrees C, around 23 or something, then what you can find, air temperature has almost nothing to do with exergy consumption rate. This is the bottom value of the exergy consumption rate, and it has almost nothing to do with air temperature, 18 degrees C, 22 or 24 degrees C. So if you are successful to make the surface temperature around over 20 degrees C, it is not the problem to increase the air temperature. That is what we could know from exergy concepts. And this is the same graph that I added the thermal energy balance of the human body as green dotted line. According to energy concept, this dotted line gives you the thermally neutral condition. According to energy concept, it is okay to have, for example, 15 degrees C of surface temperature average if you raise the air temperature over 28 degrees C. It should be comfortable. The same could happen if you raise the mean radiant temperature at 25 degrees C and air temperature a little bit below 20 degrees C. And I have made a quite interesting experiment, for example, with 30 students. I prepared 2 rooms. One has very low surface temperature, but high air temperature. And the other one, high surface temperature, but low air temperature. And ask them to visit 2 rooms and vice versa, and so on. And ask them later, in final moment, please remain in the room that you like. Almost 100% of the students stay in the latter room, which has higher mean radiant temperature with low temperature. With the concept of energy, we cannot explain why it happens, but with exergy concept, we can nicely be able to explain. So what I would like to tell you today with this example is that the thermodynamics with the concept of exergy, not so far, not very many scientists and engineers have been researching, but take a look at thermodynamics, building science, some other kind of thing, human biology, and try to make a connection. That gives you a quite new area that most of the people ignored so far, and find something interesting and also probably something very important for our common nature. That is why I gave my talk today as a title, Connective Thinking. So I'd like you to all to start thinking about something that you are very much interested in, anything by the way of connective thinking. That is what I like to talk to you. So I almost took 1 hour. So I stopped my lecture here. Thank you very much for your